Okay, I'm really not supposed to be showing you this example because it may shake your trust in statistics. So unless you're already pretty comfortable with correlation, you may want to bail out now. But here we go. We're going to be looking at these four data sets. In each case, we've got X and Y, and we've got a scatter plot of the X's and Y's. If you want to give them a concrete example, we might think of X as the dollars spent on promotions at a set of stores, and Y as the sales across those different stores. So in this particular case, we've calculated the mean and the standard deviation for the X values, the averages, and similarly for the Y values. And what I'd be reporting here is that there's a correlation of 0.82 between sales and promotional dollars spent. And if I had just told you the correlation was about 0.82, you might have imagined a picture that looks something like this. Okay? So far, so good. Now let's go over to this next picture, X and Y data. All right, well, it turns out the means are the same as before, standard deviations are the same as before, and the correlation is the same as before. That is the honest-to-goodness correlation of the X data and the Y data. However, the scatter plot here looks completely different from what it looked like over here. Whereas here we might have thought, well, there's just some dispersion in the relationship. Here there seems to be a very tight relationship, it just doesn't happen to be a straight line relationship. Here the story would be, well, you spend more on promotions, that pays off for a while, but at some point it starts to work against you and sales decrease. So very different conclusion depending on which of these two is the real story, and you wouldn't know the difference if all I had told you was the correlation. Let's go to this picture. Well, as you might have guessed, mean and standard deviation are the same. Correlation is the same as before, 0.82. Completely different situation. Here, there's a perfect straight line relationship, except for one point. This is one store that, for whatever reason, is way out of line. And maybe there's something special about that store location, or maybe this is just a data entry error. In any case, it has big implications for the relationship. And finally, last example, again, mean, standard deviation, correlation, all the same, completely different scatter plot. Here we'd be tempted to say, for example, that there might be no relationship between promotional dollars and sales, right? They don't move, and except for this one point here that's an outlier, and there must be some story that goes with that point. Again, maybe it's just a data entry error, maybe it's a very different kind of store, we don't know. Well, it's about to get even a little bit worse because I can now go into each of these, and in each case I can add a trend line, and I can add the equation to the chart. So I'm just ticking the option to display the equation on the chart. And if I do that for each of these, as you can see, the slope and intercept are essentially identical across all four examples. So if I had told you the correlation and I had told you the slope of the line, you wouldn't have known whether the underlying picture looked like any one of these four. All four of these are equally consistent with that information. The moral of the story, and this is a famous example known as Anscombe's quartet, named after a statistician Anscombe, who came up with these examples. The moral of the story is look at the data, draw pictures. It's not just enough to look at the numbers. If you really want to understand what story the data is telling, it's always helpful to draw a picture and look at the data and not just assume the picture looks a certain way from the data, from the summary statistics.